Okay, we're going to be looking here today at some postulates, definitions, and propositions for unified geometry, extending what we did in the previous weeks to include some new ideas, particularly some ideas about angles. Remember that we had over here for reference and review, we have our stuff that we covered in the first couple of weeks on incidence, and then the stuff we covered the previous week on distance and between. Real briefly, one of these propositions, properties of between, I've cleaned up since the video in the last week, and I think this is going to be the best way I can say this. We talked about this in class on Friday, and we found one of these that was incorrect. We removed it. If the distance is unbounded, any three collinear points there exists array containing, and any four collinear points actually there exists array containing them. And then this says if there's array containing them, you get these things. And so that'll work in spherical geometry if you've got if they're all on the same ray. If they're not all on the same ray, then of course this doesn't necessarily work. And of course they'll always be on the same ray by property F there. Okay, so this week what do we want to look at? We want to look at some new properties. Well, let's start with this idea of a convex set. So we're just going to define an empty set to be a convex set, and a set consisting of a single point, a convex set. And a set of at least 2 points, S, is a convex set if and only if for every 2 points, A and B in the set, the entire line segment is in the set. So if we look at this quadrilateral over here and its interior, all the blue points, then we see from the red line segment here, as long as we stay inside that set of points here, or on the edge here, all the points between those 2 points are also in the set. So it says basically if you've got 2 points in the set, all the points between them have to be in the set. Of course, we need this idea of betweenness to talk about a line segment. Here's an example of one that is definitely not a convex set, because here's a point that's in the set, here's another point in the set, and there's some points in between right in here that are not in the set, so that's not convex. Notice that if we just looked at the quadrilateral itself, it's not convex because it's not really a convex quadrilateral, because if you take 2 points on the it's not a convex set, I should say, because if you take 2 points on the quadrilateral itself, the points in between are not on the quadrilateral, they're in its interior. But if we include its interior, then it is a convex set. Okay, the convex hull of a set is the intersection of all convex sets containing S. And so we have a few propositions here that we can go over. The intersection of 2 convex sets is a convex set. The intersection of any collection of convex sets is a convex set. The convex hull of any set of points is a convex set. And the following are convex sets. We can add to that a point, a line, a ray, a line segment, and a plane. Now we have proposition 24, that's our plane separation theorem. It says if we have a line and a plane containing the line, the points of the plane that do not lie on the line form 2 disjoint sets such that each of the sets is convex and non-empty. Okay, so let's just let's illustrate that. We have a line here, and basically we have these 2 sets, the points up here and the points down here. Okay. And this is actually, we had a plane separation, let's see. Yeah, this plane separation postulate down here is very similar to it when we start talking about the sides of the point. Okay, we define the sides of the point, and those are going to be half planes, which we define down here. And we have this definition here. So remember that. If every line and any 3 points in the plane, if A and B are on the same side, and B and C are on the same, B and C are the same side, A and B are on the same side of L, then, let's see. If A and B are on the same side of L, and B and C are the same side of L, if A and C, then A and C are on the same side. If A is on the same side as B, B is on the same side as C, A and C are on the same side. Sort of a transitivity there. If A and B are on opposite sides of L, and B and C are on opposite sides, then A and C are on the same side. So we have that basic setup. Sort of a, seems like to be somewhat obvious, and that's kind of the case of a lot of our postulates. They're sort of things that seem to be obvious. Okay, so anyway, given any line of plane containing the line, the points of plane that do not on the line form two disjoint sets such that each of the sets is convex and non-empty, and if A is any point in one of the sets and B is any point in the other set, the line segment intersects the line. And so that is that separates it into the two half planes. So it's very closely related to that postulate. And I think I actually already defined a half plane earlier on the other page, so I may clean that up a little bit. Each half plane contains infinitely many points. Each half plane is contained in only one plane. Each half plane has only one edge. Every closed half plane is convex. Every half plane is convex. And each line partitions a plane into three disjoint sets, the line itself and the two sides of the line, the two half planes. Okay, so now that's just some basic setup there with half planes. Now let's talk about an angle now. An angle is going to be the union of two rays that have the same endpoint. The common endpoint of the two rays is known as the vertex of the angle, and the two rays are called the sides of the angle. We can name angles by 3 points, with the first and last being the points from different sides of the angle, the middle point being the vertex. So, illustration with the Euclidean setup. Here we go. Here's an angle, and we name it, this could be point A, point B, and point C. So we could call this angle ABC. And it's the actual set of points that we have there. That's a Euclidean illustration. Okay? So no matter where I put this as an angle, including, we will include as a possibility for an angle the same ray twice, that's called the zero angle, or opposite facing angles that form a straight line, that's going to be a straight angle. Any other kind of angle that's not a straight angle or a zero angle is called a proper angle. Now the interior of an angle is going to be the intersection of two half planes. It's going to be the half plane that has an edge, this line AB, and contains C, so that's going to be the points over here, intersected with the half plane that contains A and his edge BC, so that's the points over here. And if you look at the intersection, that's these points right in here. This is going to be the interior of the angle. This part here could be the exterior of the angle then. Okay, and of course the angle itself is neither the interior nor the exterior. Central angle of a circle is a circle whose vertex is at the center. We call this common endpoint of an angle its vertex. So some propositions that are fairly straightforward. Each angle is contained in exactly one plane. Any angle partitions a plane into three disjoint sets, the angle, the interior of the angle, and the exterior of the angle. Given any 2 points on different sides of an angle, now each of these rays is called a side. Any point between those points is in the interior of the angle. So, given any 2 points here and here, all the points between all these points, all the black points, are in the interior. Okay? And I believe this should be true in all the main geometries we've been studying. Okay. Given any angle, an array whose endpoint is the vertex of the angle, then except for the endpoint, all of those points either lie on the angle itself on the angle itself, here or here, completely in the interior or completely in the exterior, except of course for we're not counting the vertex up here, so except for that endpoint, which of course lies on the angle is the vertex. If D is a point on BA, let's go give this guy a name, D, and that one E, then angle ABC is the same angle, exactly the same angle, equal angle as DBE. Also is EBD or CBA. The order you listed is not important as long as that middle one is the vertex. If there's no confusion, if there is only one angle with vertex B, then we can just call it angle B. Given any non-zero angle and a positive real number x, there exist exactly 2 points on the angle such that the distance for those points to the vertex are both x. Given any positive real number. So given a radius here, there's exactly 2 points here, there and there, that are the same distance, that are a fixed distance from B. We can go out a fixed distance and find 2 points, one on each side, that are that distance. Two proper angles are adjacent angles if and only if they share common sides and their interiors are disjoint. So let me give another name here. There's point F. Okay, so the way we've got this, again, this is a Euclidean illustration. Angle EBF is adjacent to angle FBA. But angle ABE is not adjacent to angle ABF because their interiors have some overlapping points, like right in here. Okay, and of course some other things are not adjacent angles, like for example this angle here shares a common, it has a ray that is enclosed in this one, but it's not adjacent to that one. So among other things, they've got to have a common vertex because they have to share a side. Okay. Okay, where were we here? Okay. Two proper angles form a linear pair of angles. Again, a Euclidean illustration here. Here's an illustration of a linear pair. So they're adjacent, and they of course they share this side that I'm moving around, and the sides that they don't share, this one over here and this one here, form a straight angle, form a line, in other words. So that's called a linear pair. If you have two lines that intersect, notice that the two lines contain several different angles. They contain, there's actually multiple angles formed here. If you only count the proper angles, we have a pair of vertical angles, are here and here, and another pair of vertical angles here and here. Let's do a little color coding here. How about green for that, and then for this one, let's make it red. Now sometimes these angle markers, these are not the angles are the actual set of points. But notice we have four different proper angles formed here, also some zero and straight angles. If you take a green pair and a red pair, they form a linear pair. And if you take a green pair, that's the green pair, that's a pair of vertical angles, and the red pair is a pair of vertical angles. Some people don't count straight angles as zero angles and zero angles as angles or straight angles as angles. So sometimes when they refer to angles, we call them, what we would call those things, proper angles. Now, if we want to, now we have to talk about defining an angle measure. Okay, we'll come back. Let's come back to the next video and start there.